Welcome back to bilingual e-lectures for diploma students. This is lesson 4 on unit 5 steel structures, and so far we have seen the design of general and design of tension members and some introduction part about the design of compression members, and now we will continue. So, these are the maximum slenderness ratio for the compression members which is allowed as per the IS 800/2007. So, this is the tabular column which is taken from the IS code book, kindly refer that one. And the very important in design of compression members is classification of cross sections. And since the compression members are having thin flange elements and also some sections are having thin web elements, they are susceptible for local buckling. Then that means it may buckle locally in compression well before the calculated buckling strength of the member. Then that will affect the formation of plastic hinges with sufficient rotation capacity to enable the redistribution of bending moment required for the member before its failure. So, the very important is classification of cross sections, and based on this moment rotation character of the members, the code has classified the cross sections as plastic, compact, semi compact and slender, or in other words plastic section is classified as class 1, compact is class 2, semi compact is class 3 and slender sections are class 4. And the plastic sections are the sections which can develop plastic hinge and have the rotation capacity, in simple words, is known as class 1. And one must understand what is the meaning of a plastic hinge. A steel section, let us assume a beam section, if it is subjected to transverse load, it bends, then that means reflection increases as the load increases and the bending moment increases. The deflection reaches its maximum point and the rotation is not there furthermore on the member, then at a point along the length of the member a kink is formed, a twisting is formed. That kink or twisting is known as a plastic hinge. When the plastic hinge is formed, then that is that indicates the failure of the steel section. So, that is the meaning of plastic hinge. And if a section is capable of developing a plastic hinge and have the rotation capacity required for the failure of the structure, then that section is classified as class 1 or plastic sections. And compact or class 2 sections are the sections which can develop plastic moment of resistance, but have inadequate plastic hinge rotation capacity, then those types of sections are classified as class 2 sections or compact sections. And again the plastic moment of resistance, the moment of resistance of the section at the plastic stage is known as plastic moment of resistance. So, a section which can develop plastic moment of resistance, but it does not have the capacity to for the rotation, then that is to be classified as class 2 or compact section. And class 3 or semi compact sections are the sections which will yield, but cannot develop the plastic moment of resistance due to local buckling. So, those types of sections are to be classified as semi compact sections or class 3 sections. So, sections which cannot develop the plastic moment of resistance due to local buckling are called as semi compact sections or class 3 sections. And class 4 sections which will buckle locally even before the attainment of yield stress, that is known as slenderness sections, or that are known as slenderness sections, and this is coming under class 4. And code specifies the gross area of the section is equal to the net area of the section for class 1, class 2 and class 3 sections. So, I repeat, for class 1, class 2, class 3 sections, the code specifies the gross area of the member can be taken as the effective area of the member in resisting the compressive load. So, this point we have to bear in our mind for the design of compression members. And other classes are the buckling classes. See, buckling classes, of course, it specifies the strength of the compression member based on the buckling class, and there are 4 curves: buckling curve A, B, C and D, and buckling strength of these sections is affected by the residual stresses, initial bow and accidental eccentricities of the load. And again there are 3 terminologies: buckling class is, or buckling of the section or buckling of the element of the member is due to, probably due to residual stresses. These are the stresses remain after the manufacture of the member. So, these stresses, when I say remains after the manufacture of the member, the manufacturing process of the hot rolled sections is at a degree of around 600 to 700 degree, and suddenly it will be cooled. So, sudden heating as well as cooling takes place in the process of or manufacturing the hot rolled sections, and being thin elements and probably at the topmost flange corner will cool down first when the middle portion cools down, before when middle portion cools down. So, these type of unbalanced heat exchanges between the material parts are reason for the residual stresses. So, in simple words, residual stresses are the stresses which remain in the member after the manufacture, after its manufacturing. And the initial bow, of course, it is nothing but the bending of the member, probably due to the transportation and other difficulties. The straight of the member or straight line of the member will get deviated, and there may be some bend in the member as a whole or part of members or components or elements of the member. And again accidental eccentricities of the load, this is due to the construction issue. So, due to all these things the buckling may occur, or buckling strength of the member will get affected, and based on that buckling curves A, B, C or D and D are prescribed in the code. And classification of different sections under buckling classes A, B, C, D are given in table 10 of IS 800 2007. And again there are 2 factors, one is imperfection factor. Of course, all this imperfection factor will take care of all these deviations, that is residual stresses, initial bound, accidental eccentricities of the load, and the stress reduction factor xi is used to determine the design compressive stress from the yield strength of the material. And again this stress reduction factor takes into account the effective slenderness of the member, buckling class of the cross section and yield stress of the material. And one can refer table 8A to 8D of IS 800 2007 for the stress reduction factors. And effective sectional area AE, for class 1 to class 3 gross area is to be taken as the effective section area, and for class 4 slender members the effective area is reduced as per the provisions given in IS 801 or IS 800 2007. And design compressive stress FCD, it is denoted by FCD, and the design compressive strength is denoted by PD, and of course FCD is equal to xi times of Fi by gamma m naught, where Fi is the yield stress and gamma m naught is the partial safety factor for the material under yield, and xi is the stress reduction factor given in the table. And the design compressive strength of the member, again this is design compressive strength in the sense load carrying capacity or compressive load carrying capacity. This is load, and their load is equal to area into stress, that is all. So, strength of the compression member or design compressive strength of the member is given by the product of effective area of the member and the design compressive stress of the member, that is all. So, PD is equal to AE into FCD, and again FCD is to be taken from the table 9A to 9D of IS 800/2007, and AE of course after classifying the class of the section given, AE is to be taken, then that means class 1 to class 3 gross area is taken as net area. And how to check whether the given compression member is capable of taking the load? So, we have to calculate the design strength of the member or design compressive strength of the member, and we will see that which is greater than the design action on the member, that is PD is nothing but the design compressive strength of the member, and where P is the design compressive load on the member given. So, if PD is greater than P, then the selected member is OK. Again the design procedure for the design of compression member, classification of section is very important, that is first point, and second point design action, third point effective length, and fourth point slenderness ratio. Then calculate the effective cross sectional area or approximate area which is required by dividing the design load by its design compressive stress. And after selecting the suitable section or trial section, find the design compressive strength of the member and compare the design compressive strength of the member obtained with that of the design compressive load given in the problem. If the design compressive strength of the member is greater than the design compressive load given, the selected member is OK or the selected member is safe. So, we will take up small problems or a simple problem, not small, simple problems on finding out the design compressive strength. So, in this exercise a single I section of ISLB stands for, as you all know, Indian Standard Lightweight Beam 500. This 500 designates the height of the beam or depth of the beam at 750 Newton per millimeter, and this 750 is the numeral value of self weight of the beam in terms of Newton per meter. And again ISHB Indian Standard Heavy Beam of depth 350 at 674, this is the self weight again when they are used as columns of effective length 4 meter. Yield stress is given. Now, we will find out the design compressive strength of the first member ISLB 500, then we will find out the design compressive strength of the ISHB given. So, we will write down the geometrical properties of the given sections from the steel handbook. So, these are all the geometrical properties that are required, namely area, height or depth, breadth of flange, thickness of web, radius of gyration about the major axis ZZ and radius of gyration about the minor axis YY. And now, this is second step, calculate the slenderness ratio about the major axis as well as the minor axis of the given member, and we know slenderness ratio lambda is equal to KL by R. Here it is about major axis, so RZ. So, KL by RZ, KL is directly given in the problem. So, KL in terms of millimeter divided by radius of gyration in terms of millimeters, you will end up with a value is having no unit. So, this is 20, and similar way effective slenderness ratio about the minor axis is found to be 120. And now, the third step is to find the classification of section. For that we have to refer table 2 of IS 800/2007. In table 2 of IS 800/2007, for various classes, that is class 1, class 2 and class 3, the limiting width to thickness ratio is given, and the limiting width to thickness ratio is for class 2 it is 8.4 epsilon, and the epsilon is a coefficient, and epsilon is given by square root of 250 by Fy, and 8.4 epsilon comes around 7.67. This we can keep it, and we will find out the actual breadth by thickness of flange. So, B from the handbook we can refer the section given there. B is calculated half of the breadth of flange. So, B is equal to half of the breadth of flange and divided by thickness of flange, that is equal to 6.38. So, B by TF value is found to be, breadth to thickness of flange is found to be 6.38, whereas the limiting width to thickness ratio is found to be 7.67. So, 6.38 is less than 7.67, we will check it up, it is a plastic section, hence AG is equal to AE. I have to check whether this is class 2 or class 1, I have to check with that. I think here it should have been class 1. So, since the classes or class of section is class 1, it is plastic, hence the gross area is equal to the net effective area. So, AG is equal to AE, and the second part of that is calculation of the buckling class. For that we have to refer table 10 of IS 800/2007, and the parameter we have to find out here is depth to breadth ratio. H by BF is found to be 2.78, which is greater than 1.2, and this 1.2 value is prescribed in the IS code, and thickness of flange TF, which is equal to 14.1 mm, which is less than 40 mm. Again these two parameters 1.2 and 40 are given in the table 10 of IS 800/2007. Since these two values H by BF and TF are within the range, the buckling classes of the section about the major axis is A, about the minor axis is B. Major axis is ZZ axis and the minor axis is YY axis. So, for the section given, the buckling class is A about major and B about minor. Now, so having found the buckling classes of the given section, now we have to find the design compressive stress FCD, and for that we have to refer 9A table from IS 800/2007, and for the slenderness ratio KL by RZ 20 and the yield stress of the material which is given in the problem 300, we have to pick this value FCD from the table 9A, and it is 273 Newton per millimeter square. And similarly for the other buckling class, that is buckling class B, the FCD value is found to be 95.4 Newton per millimeter square, and this is one value and this is the other value. So, the lesser of these two values is taken. First one is FCD 273 and the second one is FCD 95.4. So, the lesser is 95.4 Newton per millimeter square. So, we will take this value for the calculation of design compressive strength of the given member, and therefore, design compressive strength of the member PD is equal to AE into FCD. AE, it is nothing but the AG substituted here, and FCD, the lesser of these two we have substituted here. So, from this the design compressive strength of the compression member is found to be 911.07 kilonewton. So, the similar way we have to work out the design compressive strength of the given other section IS HB 350, and these are all the properties taken from the handbook, and this is the slenderness ratio for this section, and classification of section again, this is for class 2 it is 9.4 epsilon, and it is found to be not class 2, it is found to be class 3 section. Even up to class 3 section we can take AG as equal to AE. So, this section belongs to class 3 and AG is equal to AE. Then this is the procedure to find the buckling class of the given section, and buckling class as per this condition or 1.2 and 100 mm, it is buckling class B about the major axis and C about the minor axis, and from table 9B and 9C the value of design compressive stress is taken for the given Fy value and the KL by RZ, that is slenderness value, slenderness ratio value, and which is found to be FCD 268 Newton per millimeter square, and the other one is 159.5 Newton per millimeter square. This is about the buckling class C. So, lesser of these two, one is 259.84 and the other one is 159.5 Newton per millimeter square. Hence, the lesser value is taken 159.5 Newton per millimeter square, and if you multiply this FCD with that of the area, we will get the strength. So, design compressive strength of the member, the second member IS HB member is found to be 1370.26 kilonewton. So, these are the answers. First section is capable of taking this much of load, and the second section is capable of this much of compressive load. And again this is the other problem, and here it is ISMB, it is Indian standard medium size beam is used, and the length of column is this, and the only difference is in the previous problem the effective length is directly given. In this problem effective length is directly not given, it is given in the form of end conditions of a column. Here it is ends of the columns are effectively held in position, not hold in position, it should have been held in position and restrained against rotation. Then that means when a end is effectively held in position and restrained against rotation, then that means the end is fixed. So, this column is top and bottom fixed, having a actual length of 5 meters. So, from this end condition and the actual length, we have to calculate the effective length based on the codal provision. So, these are the data given, and this is the simple sketch to explain what is what, and these are all the geometrical properties which are taken from the steel table, and these are all the properties that one we have to bear in the mind, because it is not similar to that of a tension member. Here we have to take many more properties from the steel table. So, time consuming is more. So, first time when you take the steel table, we have to pick all the values of the geometrical properties which are required to design a compressive strength, namely Ag, D or H, Bf, Tf, Tw, Rz and Ry, etc. And design compressive strength, this is the formula to find out that design compressive strength, and we are checking the classification of the section, and it is found to be class 1. Therefore, a gross area is equal to net area, and this is a step to find the buckling class of the member, and here it is found buckling class of the section is A about ZZ and B about YY. And again, for the calculation of slenderness ratio, we have to calculate the effective length, and this effective length is based on the end condition and actual length. For the fixed condition, the KL effective length is given as 0.65 L as per the code. So, KL is equal to 0.65 times of the actual length. So, effective length is found to be 3250 millimeters, and with this value and the radius of gyration of the given member from the table, we are calculating the slenderness ratio about the major as well as the minor axis. So, the slenderness ratio about the major axis is found to be 16, and that of minor axis is found to be 92.5. So, with these values, we have to pick the value of the design compressive stress, namely FCD, and the FCD value is found to be 136.5 Newton per millimeter square. So, design compressive strength PD is equal to AE into FCD. Substituting the relevant values, the design compressive strength of the member is found to be 1511.6 kilonewton, and it is also a similar type of problem. Here it is given as the actual length is given, end condition is given. The only difference is the built up section. It is made up of a built up section of highest HB Indian standard heavy beam with the 2 cover plates at top and bottom, and the material properties are given. Again, this is the sketch to explain what is given in the problem, and this is the I section, and these are the cover plates, bottom cover plate and top cover plate, and the properties of the handbook which is taken from the handbook, properties of the section which is taken from the handbook, and again the classification of section. For built up section, again you have to refer table from the handbook, table 2 as per table 2. For I think it is class 3, for class 3 the limiting width to thickness ratio is 13.6 epsilon, and the value of 13.6 epsilon is found to be 11.66, and the value of BE by TF external element divided by thickness of the flange is found to be 7.5, which is less than 11.66. So, the section is class 3 section, and therefore, AG is equal to AE. So, AG gross area is the area or summation of the area, summation of the I section as well as the 2 cover plates, one at the top as well as one at the top bottom. So, this is the area of the I section which is taken from the handbook, and this is the cover plate area. So, total area is found to be 18,000 odd millimeter square. And to find the buckling class of the built up section, so for built up section we do not have to find out with the regular procedure. So, for built up sections it is classified under C about both the axes. So, we will directly get into the slenderness ratio calculation, and the only thing is this is a built up section. So, for that we do not have the ready reckoner value for radius of gyration. Say all these radius of gyration denotes only for ISHB, not including the cover plate. So, by using the knowledge that you have gained in probably the engineering mechanics subject, you should be able to calculate the value of radius of gyration for the given built up section. And we know that radius of gyration r is equal to square root of IIXX by A, or here it is IZZ by A. And again IZZ is the moment of inertia about the major axis of the built up section. Again moment of inertia of the full section is equal to moment of inertia of the I section plus moment of inertia of the cover plates at the top as well as at the bottom about this major axis ZZ. So, first we have to calculate the moment of inertia or of the cover plates and add that moment of inertia with that of the I section to get the total moment of inertia about the major axis ZZ. Once IZZ value of the built up section is arrived, and already we have arrived the total area of the section, divide that and take the square root, get the value of radius of gyration. So, that is how we have to get the value of radius of gyration. So, this is a calculation involved in that. This is IZZ of the whole section is IZZ of I section plus IZZ of the plates, it is given here. And similarly on the minor axis also we have to calculate the moment of inertia, and we can take the radius of gyration about the both the axis RXX and RYY. And for the calculation of slenderness ratio we need to have the value of effective length. So, for the end conditions given, effective length is found to be 0.65 L. So, effective length is this much and effective slenderness ratio is this much, and with the help of the effective slenderness ratio and the buckling class, refer the table 9C of IS 800 2007 and pick the value of FCD. So, for some of these KL by RY values we cannot get directly the value of FCD from the handbook. For that you need to do some interpolation work. So, by doing so FCD is found to be 276.9 millimeter square, and this is the final step. Design compressive strength of the member PD is equal to A into FCD. So, it is found to be 5113.235 kilonewton. So, this is the best example, of course it is a built up section and it is very important too also. And this is a similar type of problem. Design a steel column using only difference, this is not a similar type of problem because this is a design problem. So, previous problems are dealing with only on finding the design compressive strength of the given member. So, that is analysis type of problem, and this is design type of problem. In the sense you have to select a suitable section for the given load. So, again initially we have to assume the permissible stress. Of course, these are all the steps to select a suitable section, and we have to assume the slenderness ratio. Based on the slenderness ratio and the buckling class we can assume the FCD value, and based on the FCD value and the design load we can calculate the AE required, that is the effective approximate area required. I repeat, trial section is to be selected based on the design load, and under the assumption of slenderness ratio and the buckling class pick the value of FCD. Based on this FCD value and the value of PU, find the approximate area which is required for the section, then select a suitable section which is matching with that of the area, and repeat the analysis procedure. Find the design compressive strength of the member given by following these steps, and you find the design compressive strength of the member, you compare that with that of the design compressive load given. If the design compressive strength of the member is greater than the design compressive load, then the section selected is okay and you can provide the same section. So, therefore, and for this problem we have selected ISHB 350 and this is found to be suitable, since the design compressive strength of this member is greater than the design compressive load. So, this is the first example on design of compression member. To summarize in this episode, we have taken the design of compression member introduction of compression member, what is a compression member and all these things, and the sections involved in the design of compression members, and the various types of buckling that could take place in design of compression members, and the failure modes of compression members, and the various imperfection, I mean imperfection factor and stress reduction factors, etc. And the steps to find the value of design compressive stress based on the codal provisions, and classification of sections based on the codal provisions we have seen, and finally we have also seen the procedure to find the design compressive strength of the member, as well as to select a suitable section for the given design compressive load. Thank you.